If you've ever built anything with microservices, you know the feeling, right? That pain of having to fetch data from all these different services just to get one screen to load. Well, today we're going to tear apart a really powerful pattern designed to solve that exact problem. It's called materialization, and you'll see it has a reputation for being both super elegant and, well, pretty complex. By the end of this, you're going to understand exactly how it works and when you should or shouldn't use it.
So this is the core of the problem, laid out right here. On the left, you've got the slow path. And let's be honest, this is reality for a lot of us. Your app asks for a task, it gets back a contact ID, and then it has to go make a whole second trip to another service just to find out the contact's name. It's slow, it's clunky. But on the right, that's the dream. One call, one clean response, with all the data you need right there. So the big question is, how do we get from that tangled mess on the left to the clean, straight line on the right? That's what we're here to figure out.
All right, here's our game plan. We're going to start with the problem itself, what we call the chained request problem. Then we'll introduce the materialization pattern as the solution. After that, we'll peek under the hood of the tool that actually makes this all work. We'll tackle the really tricky stuff, like data consistency, and then we'll cover what you have to do as a developer. And finally, we'll ask the big question: is the convenience really worth the cost?
Okay, first things first, let's meet the villain of our story, the chained request. If you've been working in distributed systems for any amount of time, you know this one. It's the dreaded N+1 problem, and it is an absolute performance nightmare. So let's get real for a second. Imagine your UI needs to show, say, 20 tasks from the task service. For every single one of those tasks, it then has to turn around and make a separate call to the contact service just to get a name. Think about that. That's one call to get the list, plus 20 more calls to get the details. You end up with this tangled web of requests. It's inefficient, it's painfully slow, and it leads to a user experience that, frankly, stinks. So how do we slay this N+1 dragon? Well, enter our hero, the materialization pattern. And look, this isn't just some quick hack or a temporary fix. This is a deliberate, architectural choice, and it's designed to solve this problem elegantly, right at its root. You know, when you boil it all down, materialization is really just a specific, disciplined way of doing denormalization. Instead of just storing an ID and looking it up later, you proactively store a copy of the actual data you need from that other service. The cheat sheet analogy on the slide is just perfect. It's like the task entity gets a pre-made cheat sheet with all the contact's details so it never has to go look them up again. Now this is the part you really need to hear. This pattern isn't just about making your UI a little faster. The moment your product manager walks over and says, "Hey, I want to be able to filter my tasks by the contact's last name," that's when the alarm bells should go off. Trying to join data and filter across two totally separate services at query time, that's a recipe for disaster when you're working at scale. And that's the exact moment when materialization goes from a nice-to-have to an absolute architectural requirement. Okay, so copying data around sounds great in theory, but it immediately raises a huge question. How in the world do you keep all those copies up to date without writing a mountain of messy custom code? Well, the answer is you don't. You use a specialized tool for it. In this case, the Materializer. Think of it as the engine that just automates this whole process for you. And this slide right here shows you exactly why you'd use a tool instead of trying to build this yourself. First, you're not writing tons of complicated code. You're just declaring what you want in a simple config file. It automatically handles all the tricky stuff, like events showing up out of order. Need to update all your old data? No problem. It has bulk update capabilities. It's even smart enough to automatically refetch data if a reference ID changes. These are huge, painful problems that you just don't have to worry about anymore. So let's pop the hood for a second. The mechanics are actually pretty straightforward. First, an event happens. Let's say a contact name changed event is published. Step 2, the Materializer sees that event and fetches all the relevant stuff, the contact itself, and every single task that's linked to it. Step 3, it applies the simple little transformation you wrote, something like, just grab the first and last name. And finally, step 4, it patches that new data right into the task records in the database. It's a clean, automated, event-driven flow. Of course, nothing in the world of distributed systems is ever free. By creating a copy of our data, we've just introduced a new and very famous problem, eventual consistency. So what happens if events arrive out of order? How do you stop things from descending into chaos? You know, this is the very first question any senior engineer is going to ask. In a distributed system, you have zero guarantees about the order events will arrive in. So what happens if an update from 5 minutes ago gets stuck in a queue and shows up after a more recent update has already been processed? You've got a huge risk of overwriting your fresh new data with old, stale information. So how do you prevent that?
The solution is actually surprisingly simple and elegant. It's called a sequence guard. Every single event carries a sequence number with it, like a version. The materializer stores this number right alongside the copied data. So before it writes any update, it just asks one simple question. Is the sequence number on this incoming event greater than the one I already have in the database? If the answer is yes, it's newer data, and we update. If it's no, it's a stale event, and we just toss it. It's simple, but it's incredibly effective at preventing data corruption.
And here's another really clever bit of engineering. Normally, anytime you update a record in a database, its version number gets bumped up. This is a huge problem if a user is editing that same record at the same time. Their update is going to fail because the version changed out from under them. So the Materializer does something really smart. It uses special, dedicated fields so it can perform its background updates without incrementing the main record's version number. This lets the system quietly self-correct data in the background without ever getting in a user's way. That's just really thoughtful design. So this all sounds pretty amazing, I know, but it is not magic. When you decide to use a pattern that's powerful, it comes with some serious responsibilities. So let's talk about the hard truths you have to accept as a developer.
All right, let's just lay them out there. First off, the cost of change is high. Once you materialize a field into your database, changing that field's shape or source requires a full-blown data migration. Second, that means you have to really understand your domain model and get it right first. Third, this tool only handles new events going forward. You are on the hook for writing the scripts to backfill all of your existing data. And finally, yeah, the tool handles infrastructure retries, but the business logic inside your transformation code, if that throws an error, that's all on you to handle.
And that leads us right to testing. The advice here is crystal clear. Do not waste your time writing complicated integration tests for the Materializer infrastructure itself. That's already been tested. Your job is to test your logic, the code you wrote. Use the end-memory testing tools they provide to fire off a fake event, and then just check that your transformation logic spit out exactly what you expected. Focus your energy where you actually add the value. Okay, we've seen the problem, we've seen the solution, and we've talked about the responsibilities. Now it's time to put it all together and ask the million-dollar question. Is all this powerful convenience actually worth the complexity it adds? This table right here sums up the trade-offs perfectly. To solve the problem of slow performance from chain calls, you have to accept the cost of increased storage and duplicating your data. To get away from needing perfectly consistent data all the time, you have to embrace the challenges of eventual consistency. And to get those super fast, simple reads, you have to accept that maintaining your services and changing your database schemas just became a much, much bigger deal. And that brings us to our final question, the one that every single architect has to wrestle with. Is a complex pattern like materialization just a necessary evil for building high-performance systems at modern scale? Or is the fact that you need it a symptom of a deeper problem? A sign that maybe, just maybe, our microservice boundaries, our domain models, were drawn in the wrong place to begin with. There really is no easy answer here, but it's the most important question to ask before you start copying data all over your system.